Okay, good afternoon, everyone. So it's my great pleasure to introduce our speaker today, Dr. Andrew Gettelman, who is a senior scientist at the Pacific Northwest National Lab, or PNNL. He's also an affiliate research faculty member at CU Boulder. So Andrew got his bachelor's in civil engineering at Princeton University. And then he went on to do his PhD in atmospheric sciences from the University of Washington. He's also had several visiting professor positions, including in the physics department at the University of Oxford, and also in the atmospheric and climate science department at ETH in Zurich, Switzerland. So Andrew is renowned for his work on climate model development, specifically for developing the physical representations of small-scale cloud processes, and also representing the physics and chemistry of the upper troposphere and lower stratosphere. And these models are used to inform climate policy. He's also heavily involved in evaluating climate models, so using data from satellite missions and field campaigns. And he's also served as a member of several of these science teams. And although he won't be talking about this today, he's also interested in studying the atmospheric effects of aviation and contrails. So Andrew has over 250 publications, and he's also authored a textbook called Demystifying Climate Models, which I highly recommend if you're looking to understand how climate models work from a layman's perspective. He's also got an H index of 95, and he's accumulated over 38,000 citations on Google Scholar. So here, Andrew today is going to be talking about his work on climate nowcasting. In his talk entitled Nowcasting Extreme Event Risk. So please give Andrew a warm welcome.
So thank you. Can you hear me okay? Is that good on sound? Okay. It's great to be here. It's great to come up to the physics department. Normally my faculty appointment's in ATOC, so I'm normally down on East Campus. As Ivy said, most of what I do is related to, well, I guess the branch of physics I've learned what I need to call it here is it's basically low temperature condensed matter or particle physics in a compressible fluid on a rotating sphere, which is basically just cloud physics. But the title's actually Climate Nowcasting, but working for the Department of Energy and the Trump administration, ultimately you can't use that word. So that's what it looks like in the program, and that's what it actually is. But what I'm going to talk about is, first I'm going to explain it. It's kind of a weird term, but basically what we're trying to understand is the climate of now. We know the climate is changing. I'm going to show you how we can look at that both theoretically and from data. And what it also means is that nobody really worries too much. I mean, the mean temperature, means are important, but nobody gets killed by the mean. They get killed by the extremes, or we have damage from the extremes. So it's the extreme or low probability weather events that are also likely changing. And how do we predict the risk or the probability of these things when we know they're evolving? And so climate nowcasting is essentially the probability of these extremes now over a given time window. And I'll explain why that's important and why we can't just do what we've always done, which is just take an average of everything that's happened in the past, call that the climate, look at the probabilities, and call that the probability for the next 10 years, because it's a non-stationary problem. The climate is now transient. So first I'm going to step back, because I know there's diverse backgrounds in the audience, and talk about a sort of theoretical way to define climate and climate change, sort of to illustrate it. Then I'm going to talk about how climate change affects extremes, and then get into, if we're going to try to predict what's happening in the future, understanding where uncertainty and predictability is in the Earth system, and then how to build sort of a nowcast, how to understand the climate. And then get into some of the Bayesian aspects. If we make conditional probabilities on that, we sort of have a forecast for the next decade, and we may be able to have some predictive power, and then there'll be a summary and conclusion at the end. So, okay. So what's the difference between weather and climate? The climate is what you expect, and the weather is what you get. Climate is usually considered, it's the distribution or the probability of weather, and that can be any given statistic in any given location. And weather is chaotic, right? It's actually whether chaos theory was developed by a meteorologist to describe why you can't predict the weather. Great paper, Deterministic Non-Periodic Flow by Ed Lorenz at MIT in 1961. And he had a simple model. I'll show actually an example of his model in a couple of slides. But an example of his model to explain why the weather is not predictable a certain time in advance. So here's an illustration. Here's the January minimum temperature in the 20th century at Madison, Wisconsin. And it's in centigrade. And the average of that in the middle of that broad distribution is about minus 10 centigrade. That's sort of the average January minimum. That's the climate, but the coldest ever recorded was on January 30th, 1951, and it was minus 40 degrees centigrade, which is really, really cold. It's about minus 40 degrees Fahrenheit as well. So no one gets killed by the mean. It's that weather event on the tail that's going to be really important to understand what the probability is. And you can see it happened once, and that tail is not well defined statistically, so that obviously is going to be a problem. Okay, so another way to look at this is Ed Lorenz's attractor, the sort of simple Lorenz attractor, and it's a graph of a solution of a two-variable model. You can start from very near the same place on that plot, so the two trajectories I plotted start almost identically, but end up several time steps later in very different places. So climate is the attractor. It doesn't change. It's constant. Weather is where you are on it, which can evolve very radically differently, and the probability is sort of the density of those points on the attractor. So what does climate change mean? Well, and who cares if it changes a little bit, because the weather changes a lot, so why should we worry about it? And what does that mean for extremes? So again, nobody gets killed by the mean, and there's two ways the climate can actually change. The one we commonly think of, if you think of a probability distribution. I guess, let's see. Do I have a pointer? Oh, I can get a pointer, can't I? Laser pointer. Does that show up? Oh, yeah, there we go. That way I don't have to turn around. We commonly think of, here's a distribution of temperature. We have some extreme cold temperatures, extreme warm temperatures. And if the climate changes, we get global warming, then the whole thing just shifts to the right. And you can see what that means. What was a low probability event becomes a lot more probable, and we have some events with low probability that we've never seen before, that were outside the previous distribution. And on the other side, the coldest events don't exist anymore. We don't see anything that cold. Now, you can also change the climate without changing the mean by changing the variance. And that still changes all the probabilities. Now you can get more extremes of heat, but you can also get more extremes of cold. And the probabilities increase on both ends, both tails. And of course, you're also likely to get something which is a combination of those things, where you can get a change in variance and a change in mean. And that can do things like, you can still get cold events, right? So we had a big cold event in the eastern part of the United States in the last week, where it's excessively cold. It's still excessively cold in parts of the southeast. That's not necessarily unprecedented, but it's very rare, and it still happens. And then yet, we also get very extreme warm events, and a lot more higher probability of that. Okay, so that's the theoretical definition. I'm going to show you how this works in actual data. So this is monthly mean northern hemisphere land surface temperature anomalies at every point, sort of 100-kilometer averages all over the northern hemisphere. And this is data from 1951 to 1980. I have normalized it by the standard deviation at each point, and the dimensions of the horizontal axis are standard deviation. Turns out the standard deviation is about 1 degree centigrade, so you can kind of read that as a temperature scale of about 1 degree centigrade. And the percentages sort of reflect this normalization of a normal distribution. You can see what I've defined is the very hot is more than 3 sigma, and the sort of like 0.3 to 0.34 sigma, which should be about 30 to 50% of the data, or about 30% of the data is in the sort of pink colors. And the percentages are shown there for the different sort of quintiles that I've shown you. So now let's take the same mean, the same subtraction of the zero mean, and the same standard deviation, and let's look at what happens if you go to future decades. So beyond 1980, let's look at the 1990s. That's the distribution of temperature for the 1990s. It suddenly shifted. And you can see what was a 1% probability event is now a 3% probability event. Here's another 10 years to the early part of the 21st century, and here's the last decade. So what you can clearly see is this is almost exactly what we see in that schematic picture. You have a shift in the distribution. There may actually also be a slight broadening of the distribution, but what was once a 1% probability of something greater than 3 sigma, if you define that 3 sigma based on 1950 to 1980 in the 20th century, that's now a 9% probability. It's a huge increase in the probability.
Did you say x-axis is standard deviation, but it's in 1 degree?
It's approximately the standard deviation is about 1 degree centigrade. 1 degree Celsius, yeah. It's about 1 degree centigrade. And you can kind of see how this maps to a traditional plot you may have seen of this is the average temperature over the northern hemisphere, monthly anomalies, and then a running annual mean. And you can see that's the base period here, and then that on the right is the warmer period. And you can see that shift, right? You can see it in the mean, but this is how it plays out in the distribution and in the tails and in the probabilities of extremes. And this is pretty normal, but if you look at precipitation, the changes are a little more subtle, but you can clearly see for precipitation there is an increase in the mean. These are the precipitation anomalies. This is sort of the same normalization. That's the base period. That's the black line over here. And then the green is this green line over here. Here it's a little subtle, but you can actually see it's getting broader on both ends. The variance is actually changing. This colors are outside the black line basically on both sides. So this is sort of, it's not as drastic as temperature, but it's actually more impactful because this gets to be pretty nonlinear. And you can see the precipitation distribution is highly skewed. It's much more skewed than temperature, even when you're normalizing it at every point on the standard deviation. So it's pretty clear that even this basic theory works for real data and what's happening. So what I mean by climate nowcasting, when we talk about a forecast, right, we're talking about predicting the future. So this is basically a 15-day temperature forecast, or it's in a 15-day temperature forecast. It's not quite 15 days, but basically this is a temperature forecast of temperature and wind in North America. And a nowcast is what's the current state of the system. This is the analysis. So this is actually the initialization of that same forecast run, but it's t equals 0, t plus 0. Same thing, winds and temperatures. But it's constructed with a model by bringing in all the available observations and everything we know. And a climate projection, this is on the bottom. This is 2 different estimates using 2 different warming scenarios with different CO2 levels of the temperature change regionally of the surface temperature at the end of the century. This is from the Intergovernmental Panel on Climate Change report. That's a traditional climate projection. But what is the climate now? How do we define that PDF as it's going to evolve for the next, either or centered around now or for the next 10 years, when we know even using this last 10 years is not going to give us the probabilities for the next 10 years because the climate's changing. So the new normal is that we know that decisions based on historical averages, like a 100-year flood, looking at the last 100 years, they're going to be wrong because we know the climate's already changed. And the question is, I think we can do better to quantify the current statistics or risk or probabilities of extremes. You know, what is the probability of the current low snowpack that we're having in Colorado this year, next year, the next 5 years, the next 10 years? You know, we can't just use the last 50 years and say, well, it happened 3 times, so the probability is 6%, right? We know that's not going to work. And this gets more challenging for things like precipitation. Snowfall is an example, because as I showed you, the precipitation is it's a skewed distribution, and the extremes are very nonlinear with temperature because moisture is not linear. As the atmosphere warms, the amount of moisture in the atmosphere increases in an exponential way. So we get a lot more availability of precipitation. And we know that we can't use risk based on the last 30 years. These are some examples showing extremes of precipitation. I don't even know how many sigma this would be classified. This was when they had these floods in Dubai in the middle of the desert, where you typically get 100 millimeters of rain per year, and they got 230 millimeters in 24 hours. So I mean, that's no big deal if you're in, a rainforest, but this is a desert. So, okay. So in order to understand how we do prediction, it's useful to go back and understand how we understand uncertainty with this difference in climate and weather, because the sources of uncertainty when you're trying to predict the weather and trying to either predict the climate a long time in advance or just to nowcast the climate are very different. So when we're dealing with weather, there's a lot of total uncertainty. We don't really know what the weather is going to be more than 10 to 12 or 15 days in advance with any real skill. And most of that uncertainty is what we call boundary condition or initial condition uncertainty. The weather tomorrow is conditioned on the weather today. And we have a pretty good handle based on atmospheric dynamics. We know what the state of the atmosphere is. We know which way the wind is blowing. We know where the moisture is now. We can kind of guess where it's going to be tomorrow and what's going to happen. Where we're really bad at, which I'm sure anybody who lives in Boulder knows, is quantitative estimates of precipitation and sometimes the phase of that precipitation, right? We don't know how much snow we're going to get, and we don't know if it's going to be rain or snow sometimes, but we're pretty sure it's either going to look like today or we're going to have clouds or potentially we're going to have rain or snow. The other things that go into that are model uncertainty. So the structural uncertainty in being able to understand how precipitation works and how cloud physics works, that's where we get our quantitative uncertainty in precipitation, a lot of it. And then the third one is what we call scenario uncertainty, and that's the forcing. So for example, I can pretty much tell you what the CO2 level in the atmosphere is going to be tomorrow because it's basically identical to the CO2 level in the atmosphere today. I can also probably tell you next year. I can also probably tell you in 3 years. But if you want me to tell you the CO2 level in the atmosphere in 50 years, that's not a physical problem. That's a function of what humans are doing. That's a boundary condition. It's a forcing agent on the system. So when we look at the future of climate, we look at different scenarios. And I showed you those two pictures from the IPCC. Those are two different warming levels, one higher than the other, based on putting different amounts of CO2 into the atmosphere. So that's the scenario uncertainty. And for climate, that actually dominates, right? If you ask me what the climate is in 2100, you have to know how much CO2 is in the atmosphere. And that is not something that's a physical question. That's a human system question, right? So you can see how this evolves over time. For weather, we're dealing with initial conditions. For climate, we're dealing with the forcing and the scenario. We're not dealing with the initial conditions at all. The climate of Boulder in 50 years is not dependent on the weather today or tomorrow or yesterday.
Question.
Yep.
Why does the uncertainty go down with lead time at first?
It goes down with lead time because the initial condition uncertainty drops off faster. We're also predicting different things. I'm not actually trying to predict the amount of precipitation on any given day. If we're trying to predict the annual average of precipitation, that gets a lot easier, right? So it's more, you're averaging it. And so that averaging means the initial condition, or like the expected amount of rain on any given day, that initial condition uncertainty fades over time. In addition, it also varies by, as we said, time, but it also varies by space. So what I showed you is basically sort of a global picture. And now if I'm using a lead time in years, I've cut out, say, the first year or two. So initial condition uncertainty in the atmosphere is irrelevant, but there's still some internal variability in the ocean and things like that. You're worried about an El Nino cycle if you're not averaging over it. But if you look at, a small island off the coast of Europe, for example, the United Kingdom, then things like the internal variability, the state of the North Atlantic matter a lot. And more importantly, the structural uncertainty matters. If you have a model that doesn't put the storm track in the right place in the Northern Hemisphere, you're not going to get the weather in England very well, right? And so those things can kind of change when we're trying to predict a smaller region or an individual region. And this is why when we typically do climate prediction, you want to optimize. If you're worried about the UK, you want to get a model that you know actually does the UK pretty well and does those things like the Northern Hemisphere storm track pretty well. And then the next question, which we also started to talk about, is where in the Earth system is predictability? Okay? So for the first 2 weeks, if we're worried about weather, most of that predictability is in the atmosphere. right? The weather today is mostly dependent on what's happening in the atmosphere. Now, if you start looking at beyond a week or two, then there's other things that come into play on the order of weeks to months. Yes, the atmosphere, but there's some long frequency modes in the atmosphere, like in the upper atmosphere, that govern things like the overall polar vortex that help govern the storm track, and also the land surface. For example, if you're trying to predict the weather in North America, if the continent is very wet, if there's been a lot of rain previously and the soil is wet, or if there's snow cover on the continent, that actually changes the weather, particularly downstream of that. Beyond that, when you get into seasonal, yes, the soil moisture in the land is very important, and then the ocean starts to kick in. And on an annual, multi-annual basis, you get slowly evolving dynamics of the ocean temperatures and interactions with the atmosphere, and that has a big impact on predictability. So here's a nice plot from a paper on longer timescale predictability showing it's mostly the atmosphere. It also shows that predictability goes down. Remember, we're trying to predict sort of different things over time, longer term averages, but even then, they're less certain. We're pretty certain over the next couple days what the averages of the weather is going to be, but not in the next 30 to 60 to 90 days. So the atmosphere matters, the land matters on this medium time scale, and then changes in the ocean start to be more important out to a year or so. And going beyond that, then there's some other things going on. So what I just showed you is sort of out to, this is sort of soil moisture and sea ice, this is the land surface. Now we're starting to pick up, this is the ocean. And these are sort of different terms that we have. This is sub-seasonal to seasonal, this is seasonal to interannual, and this is seasonal to decadal, out to basically a decade. By the time you get beyond a decade, that's sort of what we call the boundary value problem or the forced value problem for climate. Beyond a decade, less than a decade, there's still lots of things happening where there may be some predictability. Things like, as I mentioned, what happens in the stratosphere on the order of a month. The ocean kicks in on the order of seasons, and longer-term modes in the ocean of sort of decadal variability or annual decadal variability in the ocean beyond ENSO can also kick in the order of years. So this is important to understand. It's why when we do these things beyond just the weather scale, we typically have to do them with coupled models. Even weather models have a land surface because that's important even out a week or two to understand what happens to the land surface.
So does the solar activity come in somewhere?
Probably a little bit, but mostly through its influence on variability in the upper atmosphere. The solar cycle in energy is very, very small and is much less the internal variability. It's hard to find correlations with that. So what I'm talking about for nowcasting is sort of in the season to year to decade. Like, can we understand the statistics and the probability of the next decade? And there's two components of this. We can think of it as not a boundary value problem, which is just the statistics of where are we. On the shorter end of that, there may be some statistics and some boundary value some initial value problem statistics that we can actually sort out, which I'll talk about at the end. Okay, so how do we build a nowcast? Well, we could do it statistically. We can project these extremes. I showed you that PDF moving. Well, I could figure out the rate of that drift, and we could actually statistically kind of figure that out and move those distributions forward by extrapolating those statistics. Typically, you do this dynamically. You take a bunch of weather and climate models and you run them forward with output valid for now, and you try to generate those statistics. This gets very expensive if you want local information, and you get very subject to those local model biases, like the model biases and uncertainty. So what we're trying to do is actually now a new approach. We can basically emulate observations and use these sort of weather generators or AI-based Earth system models with forcing to develop statistics for now. And there's some benefits of this. It's fast. And if needed, we can focus on particular variables and locations without some of this of interest by using existing observations and without necessarily having to go down the route of running physical models and be subject to some of their biases. So how do we do this? We're basically constructing emulated synthetic extremes. And these traditional models are very expensive to build and run. The emulators enable us to do very large ensembles quickly to quantify the uncertainty of extreme events and to tailor it to specific needs. Most of this is happening in a project we have at PNNL, which is designed to generate variables in locations and at scales that are useful for understanding power grids, both energy demand and energy supply. And there's some really interesting ways that we're doing this. So what we're doing is we're coming up with some, did that get cut off? No, it didn't get cut off, just cut off on my screen here. So we're coming up with plausible SST analog trajectories. So starting from now, this is basically showing 10 years of an ensemble of sea surface temperature evolution. So you see the annual cycle in there of, this is global SST with some spread in it, but it's fairly constrained, but you can also see it's sort of increasing a little bit, right? Because it's a forced problem. Then we actually generate, from these trajectories, we can generate weather states with an emulator that I'll talk about that's essentially like an AI-based general circulation model or climate model. It's actually an AI-based weather model. It's not actually a climate model. I'm happy to talk about that afterwards. And then we're actually then taking this large-scale output at like 100 kilometers and downscaling part of it to 12 or 4 kilometers over the western United States to be able to run power system models. And these are distributions showing basically that this AI model can reproduce a 4-kilometer weather model and does better than essentially a large-scale weather model at reproducing precipitation. So the SST scenarios are generated by analogs. We go look at the present day, and we go into a database of climate models, and we find ocean states that match the present day as well as we can. And then we take those traces out of that archive and use them as our SST, plausible SSTs. So for example, we set it up with a current set of El Nino conditions that looks like now, and then you run it forward. And this is an example of that. What I showed you is, this is the global mean SST, and this is just blowing up that plot from before. We have 10-year traces of this. We're actually using 20-year traces. These look reasonable, and this is sort of the distribution of El Nino southern oscillation. Most of them start, except for these two, most of them start with the same distribution of tropical temperatures because that's how we condition it. And then it decorrelates very rapidly. This is sort of a known problem with predicting ENSO, but it gives us a bunch of plausible states. It's kind of easier to see if you look at the anomalies. So these all kind of cluster in the same place for the first 6 months to a year, and then we get divergence because these are sort of coupled models. And this is kind of what we want. We're starting from one state, and we actually are trying to get the statistics and all the probabilities of that. It also gives you some sense of the decorrelation time and what things might be predictable over how long. 10 years, probably not, but a year or two, there's a lot of clustering going on in these global SSTs. And what we do is we use these to generate coarse global weather trajectories. Coarse is basically standard resolution you'd see from a climate model. We're using something called the ACE2, which is AI2, which is the Allen Institute for AI climate emulator. It's basically an autoregressive weather generator, uses a limited set of prognostic variables, and produces essentially 6-hour output on 8 vertical levels and things like precipitation, surface temperature, surface pressure. It's stable, and it can reproduce the present climate. And we use this to generate rapidly very coarse weather trajectories. So this actually runs on our cluster at PNNL using one GPU node or one GPU chip. Takes 3 minutes to run a year. To take the underlying, say, take a general circulation model at that resolution would take about 250 CPU processors on the order of 30 to 40 minutes. So that's thousands of times more compute. But we get about the same quality based on the large scale that we're producing. And then we can do multiple ensembles of weather states. We can generate lots of statistics. And then we're actually downscaling this with a diffusion model. So this is an AI model that we train it by looking at a large-scale average field that is used to drive a mesoscale model for the western United States this one's 12 kilometers. And then from the large-scale field, we build an emulator to get to the 4-kilometer field. And this is just a trace of surface wind at one particular point. And what it shows is that we're actually, the large-scale weather is the blue line, and the 4-kilometer model weather that we've essentially used as the target or the training is the black, and then the red is the AI model that's able to do that. And if you look at the solar, for example, looking at solar insolation, which is important for solar power, we can actually look at the correlation between the actual weather model at 4 kilometers. The blue is the large-scale 100-kilometer weather model we put as the input. You can see that actually has a bias, but that's corrected when we use the downscaler model. We can actually do a pretty good job of getting the correlation for things like solar insolation. We can also do a good job. This is the same thing, but percentiles of precipitation, and this is it shown in the PDF that I showed you before. So we can actually downscale this pretty effectively. Now, running a 12-kilometer weather model for the Western United States would even be more expensive than trying to run the climate model. Or running a global 12-kilometer model would add probably another order of magnitude to the time it would take to run a CPU model. And then this is looking at just seasonal averages over the central United States, where we're getting about the right range and distribution. There's a few biases in here with the means. Those are the hash marks in the middle. But in general, we're doing a pretty good job of getting these distributions correct. And if you look at these are mean precipitation maps showing that there's 2 sets of observations. This is our target. This is the evaluation data, which is another high-resolution model. And this is our downscaled data. If you look at the difference to one of the data sets, we're actually not doing that badly. These are sort of small differences of maybe 10%, 10 to 15% of the total mean. What's more important is looking at the extremes. So this is sort of the distribution, the PDF of precipitation intensity. And you can actually see out to the 99 or 99.9 percentile, which is rainfall in terms of upwards of 100 millimeters a day, which is very high. We're actually reproducing the distribution curve and the frequency quite well. And that's also shown here. This is the value of this 95%. This is how much precipitation is the 95th percentile. This is one of the observations, and these are the different maps where we're getting the actual downscale data is producing very low bias in this metric, which is good. It actually is pretty remarkable how well we're able to generate these statistics for the historical period, which gives us confidence that we can actually generate synthetic traces for the near future also pretty well. So we think we're able to now generate some of these nowcasts and come up with probability distributions with large statistics. But what if we're not worried about the next 10 years, but what if we want to know what's going to happen in one particular year, in a couple of years from now? Can we actually do 2028? Can we figure out what the snowpack is going to be in Colorado in 2028? Well, the answer is no, because we don't even know what it's going to be for 2026. And that's another story, as most of you know. But maybe there's some statistics in there that can give us some probabilities. So we think we can do this for the now, but what if we want the next couple years? Is there any useful predictability? So, like, for example, we know if there's a La Nina cold event now, what does that mean for this year, next year, 2028? And how can we actually do that? Well, we want to know if this impacts extreme weather and how much skill is there. And the skill we're looking for is kind of interesting. It's a little different. It's a conditional probability. This is a Bayesian problem. Given the total possible, say, nowcast, and given the current conditions, how much can we actually constrain our envelope of probability, and how much does the tail change? So initial condition uncertainty is sort of the problem in weather forecasting. So this is an example of weather forecasting, but it works with this problem too. Here you have the total climatology. This is sort of all possible weather states or the whole climatology of possible states of, say, extreme events over Colorado or possible snowpack amounts. And given where we are now, given a current condition, what is the conditional probability of where we could get to, where those trajectories could take us? Because in general, it will be smaller than the whole set. Now, if we go out to the whole 10 years and we average over that 10 years, we should get identically back to this climatology. but how much is it actually predictable? And that is a non-stationary thing. So this is one of my favorite examples. Different states have different predictability, okay? Sort of intuitively obvious, but this is a forecast for London, and it's from the 1990s, but that's okay. And it's for initialized on the 26th of June, 1995 here on the left. And on the right, it's the 26th of June, but it's the year before. And what you can see is this was a nice warm summer day of 24, 25 centigrade. That's like, you know, in the high 70s. It's pretty nice. And that was pretty constant. And the red lines are the different ensemble members of a forecast. The black line is the control, the best estimate. And the dashed blue line is what actually happened. And that's a pretty tight constraint, even out a week to like 6 days or so. You know, it could have been from, now it's saying it was something like between 75 and like 60 or something like that. If you go to the year before and look at the same day of the year and look a week in advance, that's pretty much any season you want in London, right? This is 95 degrees to 50 degrees Fahrenheit. It's a big spread. And the ensemble's all over the place. And what happened is kind of all over the place, but on the cold side of that. So these different states are very different in their predictability. It would just be good if we knew this, right? Because the variance is very different. And this is, theoretically, this works in the Lorenz attractor too. So I can pick 2 points, weather 2 and weather 1. So if I pick weather 2, which is the solid and the dashed blue line, that's in a place where both those things, the same distance apart, will evolve the same way on the attractor, and after some given time will be right next to each other and not diverge. You can do 2 other points which are not far away, and which are separated by the same initial distance, and you can end up bifurcating into some very different states over the same time window. So that's one of the things we have to also take into account, because it's a very nonlinear system. So how do we predict this future? Well, climate prediction is the distribution. It's the PDF. We average over a time window, especially the extremes. Nowcasting is recognizing that the climate's changing, so we want it over some finite time window that we hope to define, usually in the near future. Weather prediction is the possible envelope within that climate prediction, or within the overall climate. And a seasonal decadal prediction is just extending that to very long time horizons and averages over a season or a year. So how does this nowcasting PDF change given the current state? And this is the Bayesian problem. It's the conditional PDF. Can we understand that? And again, the forecast lead time for weather forecast, we get excellent skill to no skill for individual events. The subseasonal forecast, we can get some idea of averages of is it going to be wetter or drier. And then seasonal forecasts, again, less skill in is it going to be wetter or drier, and what can we actually predict over long periods of time. So beyond 2 weeks, we lose specific skill. We're mostly just making probabilities and distributions. And one thing that we try to understand, which is more of a human problem, is just because I can tell you there's some statistical significance in a prediction, it may not be actionable or useful, right? And this extends to seasonal predictions out to about a year. We can do modes of variability like El Nino. The patterns of warm and cold in the Pacific govern, in particular in the western United States, how the storm track works. They may not work that much well for Colorado, which I'll talk about. We don't even know if the skill extends beyond a year. And it's likely there might be some skill, but it might be state dependent and it might be region dependent. And because some states are more predictable than others. So even if we could know what states were more predictable, that would be useful for us. And even this skill may not be actionable. So a low probability of more precipitation next year may not mean anything to anybody. We may not be able to act on it. If we have a high probability, yes, but we may not have that. So I'll show some examples that are actually being used, or 2 examples are being used today, one that's a research example. This is a seasonal forecast. It's from something called the North American Multi-Model Ensemble, the NNME. It's produced by NOAA. It's the probability of wetter or drier conditions with a 6-month lead. This is for June, July, and August. And it's based on coupled models, initialized now, run 6 months in advance. And it's based on about 6 or 8 models, and it's a fairly simple statistic. It's the fraction of models that show above or below average or neutral amounts of precipitation. So you can see this is when models, these are the locations where models are agreeing, and the intensity of the color is how well they agree. So it's pretty moderate. Those medium colors are about half the models are saying it's going to be wetter, significantly wetter, and or half of them are saying it's going to be drier. But again, how do you use this? Well, if they all start to agree, you settle into a pattern, and then maybe that actually has some skill. Wintertime skill in the western United States in this tends to be larger if you have a large El Nino event, a large El Nino signal in the Pacific, because that has more control over the storm track. Getting to El Nino, this is another example. This is a multi-model El Nino forecast. So this oscillating pattern of warm and cold sea surface temperatures in the Pacific moves the convection across the Pacific or back into isolated parts of the Pacific, and really changes the storm track in the western United States. During a La Nina period like now, the storms tend to track further north. The Pacific Northwest gets water. During El Nino, it more hits California. Colorado sees some node in that between the northern and southern parts of the state. The correlations are not as high, but we tend to get a similar sort of balance here. And this basically is sort of the current state of El Nino. It's a cold event, a moderate La Nina. And you can see significant spread in the models. These are rolling 3-month periods, even a couple months in advance. And then really by the time we hit the spring or the summer, by the time we get to fall, it could be, some models are saying it's going to be a pretty strong El Nino warm event. Others are saying it's still going to be a moderate cold event. They're all tending in one direction, but there's huge spread here. So there's not a lot of useful information. Part of this is because there's a known spring predictability barrier in El Nino. If you looked at this in November, or if you looked at this in September, we're much more certain out through next winter. So we have more like a 9-month window in the fall, but in the northern hemisphere spring, we can't really predict into the summer very well for El Nino, just because of the seasonal dynamics of the system. But we may be able to get slightly better by mining large amounts of statistics in some of these coupled, both simulations and observations. Then some people are trying decadal prediction. So what this shows is the skill in decadal predictability on a 5 to 9 year window, which looks pretty high. It's like an anomaly correlation between what actually happened and what's predicted in hindcasts, although that's because the temperature here doesn't change that much. This is actually the map of the change in the anomaly correlation of coefficient due to the actual prediction. And most of these correlations are not that high. There's pretty much less, this whole scale is less than 0.5. So we're not actually getting a lot of predictability here, and increase over essentially persistence. So this is from something called the Decadal Prediction Large Ensemble, and it's coupled models where they spin up the ocean not with observed observations, but by just forcing it with the atmospheric observations. It's very strange. We have lots of observations of the ocean that they're not able to use because the ocean models are so biased they get an initial shock that outweighs any signal. So there's a lot of development needed of ocean models. It pretty much is not working very well because of this. We can't really get at the predictability because we can't even initialize the system reliably. So if we want to look at decadal prediction, the sort of nowcasting approach may actually have more, there may be more utility in it. So what I've done is this is the land surface temperature for winter in the northern hemisphere. And so it's slightly different than what I've showed you before because it's seasonal. But here's this 1951 to 1980 mean again. And then here's this where it's warmed up. So this is the last decade. And then this yellow line's kind of interesting. I've just taken those periods in the last 20 years with El Nino warm events during winter. So it's a conditional probability. And you can actually see that you get a very different peak. You get a slightly different mean because the distribution is skewed. And actually, the variance is slightly larger. So it's a very interesting problem. And it's a research effort to figure out, can we actually use information like this with the nowcasting approach, looking at the next 10 years and the current conditions to figure out where we may have some predictable, some skill in this. And so I'm going to finish up with one or two ways to come at this. So we have this deterministic ensemble prediction, which the land surface matters on the seasonal scale. Ocean models are very hard to initialize properly because we don't have enough data. And the ocean energy cascades and scales make prediction harder because it tends to happen at smaller scale, and it's very difficult to get observations there and get the dynamics right. So the decadal prediction illustrates all these flaws. And we can do statistical forecasts. Some of those ENSO models were statistical forecasts, but that assumes the climate isn't changing. So if you're using a statistical model of El Nino built on the past, that's not necessarily going to work very well for the future because it's a slightly different climate. So we've explored using some of these emulators and this conditional probability where we essentially develop a nowcast, and then we're trying to look at the current state and figure out, can we actually come up with the conditional probabilities of that? And this, again, what I showed you before is we're building our nowcasts, and in this first couple years, because we're conditioning all these sea surface temperature traces on now, we actually have some convergence that maybe there is some skill for a couple years in here that we actually are going to try to mine. So we're currently developing this capability. Another way to do it was to try to use AI to emulate the extremes directly. So what we did here is we took a metric of a bunch of different extremes, things like what's the maximum, and what I'm showing here is the maximum 5-day precipitation. So we're not looking at the mean at all, we're just looking at the maximum 5-day precipitation. And we go back through the observations and we construct essentially, we figure out what the maximum 5-day precipitation is, and then we train an emulator on a lagged precipitation. So we asked the emulator, given anomalies now, what's the maximum 5-day precipitation in 6 months? Which is a bit wacky way to do it, but what it does is it allows us to use those NNME forecasts of precipitation anomalies to match in the historical record what happened 5-6 months later. And we did some preliminary tests of this, and they're actually very suggestive. So here's a forecast that we did a year ago in January of 2025 from March to May of the maximum 5-day precipitation in South America. And here's the percent anomaly from March to May. And this is the verification. And this project was essentially was collateral damage in the restructuring of the Department of War, where they canceled all their environmental research, so we never really got to go very far on it. But in preparing this talk, I actually did some verification. I went and got the station data for April 2025 to do verification, and it's not totally out to lunch. We actually seem to get some response in getting the precipitation gradients. You can see Central America is dry, the northern part of South America in sort of Venezuela and Colombia is wet, and the rest of the continent is sort of mixed with a little bit of dryness in here, particularly in the southern part of this. So there may be some opportunity to use AI to try to mine some of these things and come up with new ways of actually doing this. So I'll finish up with a couple of final thoughts related to this. So I think we may be able to advance decadal prediction with AI methods, particularly in a couple of ways. One is that we can use emulators, and I do think the AI methods and the emulators have different ways they're going to actually probably significantly improve our ability to do even deterministic modeling and physical modeling and hybrid modeling of the system. Data assimilation and bias correction, or entire model emulation for the ocean, is showing real promise in getting rid of some of these ocean biases and allowing us to initialize oceans with the actual observations. If we could do that, I think we'd get much better at a couple years of prediction. Large ensembles are needed to generate robust extreme event statistics. We can construct storylines around particular synthetic events and found in these ensembles, and we're doing that right now. We're generating hundreds of years of synthetic data to build these nowcasts. And coupled Earth system emulators, we're using an uncoupled atmospheric weather generator. Coupled emulators of the Earth system are on the way. They're being developed right now. And then some states are going to be more predictive than others. Sometimes a 2-year forecast is going to work, and sometimes it won't. And the key is knowing, can we tell the difference of when we have skill and when we don't? So for example, decadal predictability may not be actionable. La Nina events, what we have now in the Pacific, typically brings colder, drier winters to southern and eastern Colorado and above average snow to the northern mountains. And how's that working out for us this year? Not very good, right? That's not necessarily something that might be actionable. So it takes a lot of work with stakeholders. One of the advantages of the last thing I showed you, which was focusing on emulating specific extremes, is we can work with stakeholders to emulate specific events that they're worried about, like extreme precipitation or extreme dryness or aridity, and just focus our statistics on that. And that actually has quite a bit of power in using AI to maximize our ability to mine the data and mine synthetic data that we can produce as well. So summary, the climate has already changed and is still changing, so we can't rely on past statistics of the future. We need a blend of observations and models to nowcast the current probabilities over the next 10 to 20 years. And this is a new way to think about current climate. It's sort of nowcasting the evolution and an evolving current climate. And then data-driven methods can accelerate our ability to provide robust extreme statistics at fine resolution and to focus on problems for particular aspects of society that are important. And I think similar methods may be able to help us understand the Bayesian or conditional problem of within that nowcast, what do we learn from the current state and how far can we take that forward? There's lots of opportunity and promise. I don't know that decadal prediction is going to be useful, but I think certainly in the seasonal context, there's a lot more that we can do, and I think we've got some new methods to actually try to do it. So, thank you.
Questions for Andrew? Leo?
Yeah. Yeah, so when is the next Power Day?
3 weeks from Thursday.
I guess that's weather, right?
Yeah.
So, no, so you, I think in your data you were showing that over a decade, average temperature shifted by a degree, or what was the?
The recent decade, yeah, but the warming has been nonlinear, and the warming over the last 20 years has been very episodic and nonlinear, and it warmed quite a bit. Let me get to that plot. So here, you can see there's a real jump in here, right? And so this warmed, it's more like half a degree. Well, let's see.
So I guess what I was,
Yeah, this is actually from 1950 to 2023. It's like a degree and a half.
And
It's not one decade. That's a span of several decades from the base period.
and how does that compare to the standard deviation? You know, like you were talking about these two, the distribution is changing and kind of the average is changing.
Right.
Changing and the standard deviation is changing. How do those compare? What is dominating the change?
This is obviously dominated by the increase in the mean. It's a good question to go back and to cast this in terms of standard deviation and look at how that's actually evolving and what impact the change in standard deviation has on the statistics. I haven't actually looked at that. There's not much impact for temperature because it's somewhat normal, I think. There's a little bit of spread, I think, change. There's obviously an impact on precipitation. You can see that widening and the skewness of it. So, but that's a good point. I could actually use these statistics to pull those two things apart. We haven't done that yet.
Question?
Yeah, what do you think the potential is for using this methodology for predicting risk of achieving tipping points, where I think of those as being effectively the attractors themselves shifting?
If we understand what those tipping points are going to be, fine. If we have them in observations or we can simulate them reliably in models, then yes. But these methods are sort of data-driven and underlying, they're only going to capture what's in a dynamical model or what's in the existing observations. So they're good for thresholds, but they may not be good for tipping points, because tipping points are inherently sudden changes in, as you said, that whole attractor. And if it's robust and we know, or there's ways of simulating that tipping point in models, then yes, we can try to mine the conditions across a multi-model set. And for certain things, like if you're talking about tipping points for ice sheets and other things that are evolving that we know about, yes. If you're talking about things where we don't understand the fundamental physics, like release of methane from subsurface clathrates, that's probably not going to be something this method is quite as good at, I would say.
Question?
Yeah, my question is kind of two parts. You mentioned for the decadal predictions, you had a hard time initializing the ocean models.
Yep.
And then it seemed like later that was related to not having good ocean data.
It's actually related to the model, not the data. We have more data than we can use. Like when they initialize those ocean models, they can't use any subsurface ocean data. And another way to think about it is we make analyses of the current state of the system. We do that for the atmosphere, and it's pretty reliable. You can initialize an atmospheric model with any of those analysis states, and they work pretty well. But when you try to make an ocean analysis, you're filling in so much data, and the ocean dynamics are dependent on that data, where the thermocline is. It's all kind of, and the scales in the ocean, the length scale is smaller. And the eddy cascade, the more energies in the smaller scales. So initializing an ocean analysis, the analyses are vastly different. And if you take an analysis and apply it to as an initial condition in an ocean model, the model just goes where it wants to go. And it's a bigger shock than the signal, so you can't really actually do that, which is why the way that they initialize these systems is they take the ocean model and they run it for 50 years forced by the observed atmosphere. And then they use that. So there's never any ocean data that goes into it. It's all just atmospheric data pushing it. And then they let it go because it doesn't have a shock as much. But it's, you can see how that's problematic because we know a lot more about the ocean than we're able to put into these systems. So I don't think, and the nice part is that some of these AI methods allow us to use the data to correct the biases in the modeling for the ocean. And we're starting to be able to do that. And I think that's going to be the biggest advance for these things in the next couple of years. The atmosphere is getting pretty mature because we have a lot of data and we understand it a lot better because we live here.
Other questions? Yes.
I think you mentioned like using AI methods, and I usually think of those as like black boxes kind of. And is the idea that you don't necessarily care how AI is able to get the results themselves?
Oh no, we care how it gets results. So a lot of these things we extensively test and probe the AI methods because there's different ways of building, an emulator is a black box, but it doesn't mean if you know what you're doing, you can't get information out of it. So the weights in that black box and how they affect different variables in different locations, you can probe that black box and understand how your inputs are mapped to your outputs. Like if you have a emulator which is location specific, you can figure out if you're coming up with an output, what variables and what locations were most responsible for that output. So we do a lot of that of what we call explainable AI, which is probing the emulators to understand what they're doing and to try to make sure that it makes sense to us. Yeah. And that's the difference is, a lot of these large language models, we just use them as black boxes. But all these emulators are generally custom built and custom trained. So we have control over understanding how these things work. And there's a lot of time spent in understanding the different methods. There's new methods being developed all the time. But we have ways of verifying and testing all these things. And it's standard both doing it externally of just looking at test data and then also internally of probing the weights in the emulator structure itself.
Any other questions? Last one.
Thank you, Andrew, for this talk. So the comment concerns the problems with the ocean models. So in some recent studies that looked at seasonal forecasts, like based on the ceasefire, that we see at the level of ceasefire, actually they find that there is this sudden, very
Right. Well, yeah.
So then of course, if you couple the system, you also probably the error resolution.
Right. I mean, the atmosphere is not blameless in all this, but yes, then that also, it's just the coupling of the models together is also problematic because in many cases, the way that we do the coupling is an approximation, and in some cases it may be wrong at different scales. So that does add a lot of complexity to it. And yes, the coupling between the models is another area where people are working on not treating it as a solved problem, but that there's a lot of work to do on it.
Okay, let's thank our speaker once again.